Welcome to ECE 1220 at the University of Utah. Today we are going to learn about using supernodes to solve for special situations in the node voltage method. So why do we need supernodes? Let's look at this circuit below. So normally I would say we're writing a node voltage equation for this node voltage N1, and notice that this website they were using N instead of V for their node voltages. And then there's a second node voltage over here, N2, that is unknown. And so if I were to try to write an equation relating currents at N1, I have 3 amps coming in here, I have some amount I1 coming here, I have some amount I2 coming here. Now where we run into a problem is normally the next step in our node voltage method is to turn the currents into a voltage using Ohm's law, I equals V over R. But in this case, we don't have a resistor there by I2. We have a voltage source, which could have any current. So what do we do in that situation? Well, we use something called a supernode. So supernodes combine multiple nodes around a voltage source into kind of one giant node when you're doing node voltage method. And Kirchhoff's current law will still hold even for that circled 2 nodes together. So Kirchhoff's current law, actually it turns out for any area in space, I could have wires coming in and out. And even though these are 2 separate circuits I drew here, right? And they're just wires coming in and out, so it's the same current flowing in as out. So even though I drew the circle for KCL surrounding 2 completely different circuits, it still all sums to 0, because if this is 2 amps going in, 2 amps going out, 3 amps going in, 3 amps going out, then I get 3 minus 3 plus 2 minus 2 equals 0. So same thing holds with our supernodes. I can draw a circle anywhere in the circuit, and any currents flowing out of that circle must be equal to all the currents flowing into that circle. So here's some examples of supernodes circled in a circuit. Notice that they even included the resistor in this one, and that's fine because the current coming out, the current coming back to this point, they just cancel each other out. And just to reiterate, right, we need a supernode whenever we have a voltage source that has a non-constrained current. And so we can't write a KCL equation, or we can write a KCL equation for it, but we can't write an Ohm's law to replace those KCLs. And using supernodes is also helpful because it will reduce the number of equations we ultimately need to solve for the circuit. Because I could have, back up here, I guess I could have just created an equation, a third equation essentially, and kept I2, but now I have the 2 unknown nodal voltages, an equation for them, plus an I2 current equation. So that's just too many things going on. So let us try finding supernodes. So here in this circuit, they've gone through and they've labeled that these are the 3 unknown nodal voltages that they're going to solve for. Why didn't they mark here? Why didn't they mark here? And why didn't they mark there as unknown nodal voltages? Well, the one on the left here we know is 50 volts. The one right here we know via the 3 amp source being in series with the 7.5 ohms. So we know the voltage across this one is 7.5 times 3. So it's technically known. And then this one over here kind of relates to C. It's VC plus 25 at this node. And that's kind of a clue for you when we're making supernodes. If you ever have 2 different nodes labeled with the same variable. Let me do this in a different color. So this is labeled VC, this is labeled VC. That's kind of a hint to you that you might be using a supernode. So I will circle now in red, I guess. So here's one supernode that I am going to use to solve for this circuit. Oh, and we're missing one more node, aren't we? This one in between here. So why didn't they label that one? Again, we can trace through the voltage source right here and see that this is VB minus 10 volts. And again, because I notice that I'm using VB to define both of these nodes, then that kind of indicates to me that this is going to be a supernode also. And I'm going to look at all the currents flowing in and out of that supernode. So my final question to you is, why do we not need a supernode for the 50 volt source? The reason we don't need a supernode for the 50 volt source is on one side it has ground defined. So there isn't an unknown voltage on one side. So therefore we can directly define the voltage on the other side as being 50 above 0. And we know the voltage, and thus it doesn't need to have a supernode in this case. But if, for example, this resistor wasn't here, then for solving for VA over here, I would need to use a supernode somehow, because for this branch, I don't have any known current. Okay, let us practice this one more time. And this time we're going to have to draw our ground at unknown nodal voltages ourselves. Okay, so I chose ground at the bottom like we often do. And then I'll label this one over here Vx based on this right here that we're desiring in the end. So tracing through from ground up through that plus Vx and the 1 kilo ohm. I know that this nodal voltage would be Vx. Then tracing through this voltage source here, I get Vx plus 6 volts must be the nodal voltage here. And notice again, because I have Vx on both of these, it's a good indicator to me that I'm going to need a supernode across. And then let's label our other unknown ones. Well, this one is known, traced through ground, plus 10 volts. And then finally, we have this node over here, and I don't know what that one is. So I'll name that one VB, I guess. So in this case, we have two unknown nodal voltages, and we've circled a supernode that we're going to need to solve for this circuit. So now let us actually write equations for the circuit. First, I'll write an equation at supernode, and then I'll write an equation at VB. Actually, you know what? Let's do VB first, because we did that last lecture. We know how to do that. So sometimes when we start getting circuits with lots of different unknown nodal voltages, instead of drawing a million current arrows on the circuit, you might actually just draw, say, all currents going in or all currents going out sum to 0, and then just skip writing out the I1 plus I2 plus I3 equals 0 step. So that's what I will do today. So for currents going in, they're all going in, they're going to sum to 0, and then I replace each with V over R. So voltage on this side, in the direction of the arrow, right? This side minus the side towards the direction the arrow is going. So in this case, we'll get Vx minus Vb all over 2 kilo ohms. For this path, we have Vx plus 6 volts. I'm not going to put the volt there. We might think that's a variable. minus the VB all over 6 kiloohms. And then finally, VB minus ground is 0 all over 4 kiloohm. Okay, now let us go look at the supernode. So flowing into the giant purple circle, sure, we'll do everything going in. So let's draw current arrows. Oops, I'm trying to erase all those. So here's my supernode right here. And then I'm going to do all the currents flowing in to the supernode. So this is technically flowing in, this is flowing in, and this is flowing in. Okay, so from over here, we start on this side, so 0 minus Vx over 1 kiloohm. And we're going to sum all of them to 0 again, because we're doing all pointing in. Vb minus Vx for this arrow. Vb minus Vx over 2 kiloohms. And then we're going to do this current right here, so we get VB. And notice I used the nodal voltage that was over there, and in this side, in the supernode, I still am going to use the separate nodal voltage within the supernode, depending on where the current's flowing in. So this one's going to be VB minus Vx plus 6. And don't forget that that negative is going to be distributed to both. And then finally, that's going to be over 6 kiloohms. Didn't leave myself enough room here. We'll erase that minus 0 for now. Final step will be from this 10 volt node over to Vx plus 6. Again, it distributes all over 5 kiloohms equals 0. So that is how I made my 2 node voltage equations in this situation where I have a supernode. I think you're ready to do the worksheet now.